Okay, so here we are on our very last lecture of the semester and also our last lecture on the special senses. I apologize, this took me a little bit longer to get posted. I had some computer issues, and as you can see, the file format had to change a little bit. So I apologize because the original portion of the special lecture, the special senses lecture, the part kind of A to it, um, I don't have the PowerPoint file anymore. For some reason, that file was corrupt and I had to recreate the file. The original portion I did have saved as the PDF file for you. So unfortunately, we just have to kind of go with the PDF file for the first half of this. And then I did recreate the PowerPoint file for hearing and balance for you. So let me know if you have any issues with those files or the file formats, and I will do my best to get it to you in a file format that is functional and hopefully not corrupt. So here we go on the second part of the special senses. This is all going to be about the ear. And so we're going to be talking primarily about our sense of hearing and our sense of equilibrium or balance. And here's my, of course, funny meme for you because, what would be a lecture here, an anatomy lecture, without some type of funny meme? So you can go ahead and read that. We're going to be talking about the anatomy of the ear. And so because some of my lectures are a little bit longer because I don't have you for lab, so I will kind of briefly walk you through the anatomy of the ear. Again, I'm not going to have you label parts to an ear and the different regions of the ear because that would be more lab. But I do like to walk you through the parts just that you know where the parts are when I'm talking about them in the rest of the lecture. So just as a heads up, I'm not going to have you label anything for lecture. So if you see here on the external ear here, we're going to have what's called the auricle here. And the auricle is going to kind of funnel the sound into here. This is called the external auditory canal, or again, you'll hear it called the external acoustic meatus. Both of those terms are correct, and I think your book uses external acoustic meatus. But again, either term's correct. You'll see different books will use different terms and different different physicians and medical professionals will use their favorite term as well. It usually has to do with whatever they learned. So again, external acoustic meatus or external auditory canal, again, they're the exact same term. Okay. So basically, again, that auricle is going to funnel the sound into the external auditory the external auditory canal or the external acoustic meatus down towards the eardrum, or what we're going to call the tympanic membrane. Okay, now that tympanic membrane, I'm just kind of going through this in the format of kind of how sound is going to be kind of conducted, and then we'll get into the nitty-gritties. But the tympanic membrane is kind of the border basically between the external ear and the middle ear. This is going to be the middle ear right here, and then this will actually be the inner ear. So that sound will then come along here and be transmitted. Those sound waves will be transmitted into vibrations at the tympanic membrane. The tympanic membrane then is attached to these three inner ear ossicles. Those are our inner ear bones, the malleus, and you might remember this from the beginning of the semester, the malleus, the incus, and the stapes. So basically these inner ear bones are going to kind of amplify those vibrations. And then they're going to basically transfer those vibrations into kind of pressure waves in a fluid that's going to be found in the inner ear. Okay, so now this is going to be our kind of point we are defining border between the middle ear and the inner ear here. So here, the stapes is going to meet up with what's called the oval window on the vestibulocochlear apparatus here. And so it's actually on the vestibule. And what's going to happen is now these vibrations are going to be transferred at this oval window into pressure waves, into this fluid that's going to be found all inside your inner ear and inside the vestibulocochlear apparatus here. And so then those vibrations, the pressure waves will then make their way and move through the cochlea, where they're actually going to stimulate our nerve conduction. And we'll talk exactly about how that happens. Once that happens, then nerve conduction will be sent through the cochlear branch for hearing of the vestibulocochlear nerve. So now you know why it's called the vestibulocochlear nerve. And again, this is cranial nerve number 8. And that's because it has a branch for the cochlea, which is going to be associated with our hearing, our sense of hearing, and then the vestibule, which is going to be associated with our sense of equilibrium and balance. Okay, and so it's got a vestibular branch and a cochlear branch that come together to form the vestibulocochlear nerve. All right, so that kind of gives you an overview of some of the major parts to the ear and how we kind of break down the ear from external, middle to inner ear. So again, this will be the middle, and then this is the inner ear with the vestibulocochlear apparatus. And this is going to be housed, again, primarily here in the temporal bone. One last tube here that we'll talk about, it's called the auditory tube. It also used to be called the eustachian tube. And we'll talk about how it's important for kind of equalizing pressure in that middle and inner ear. Okay, so again, the ear has these 3 major structures. We talked about the external ear, the middle ear, also sometimes called the tympanic cavity, and then the internal or inner ear. The external ear is going to be primarily dedicated to collecting sound waves. So again, that's what that pinna structure is doing. It's kind of collecting the sound waves and funneling them down into, again, that external acoustic meatus. The middle ear is going to be dedicated for hearing only. So you're going to, again, have this kind of small air-filled cavity inside the temporal bone that is going to contain all of these things for the middle ear. The auditory ossicles, which is going to be, again, the malleus, the incus, and the stapes, the oval window, and then the round window. Okay, so that'll be the middle ear. And then the internal ear is going to be associated for both hearing and equilibrium, because this is where you have that vestibulocochlear apparatus. So again, it's going to have inside the vestibule and dedicated for equilibrium, and the cochlea dedicated for hearing. And in that vestibulocochlear apparatus, inside there is going to be this kind of labyrinth of membranes and fluid that's going to move through this kind of complicated series of canals, and we'll talk about how that happens. And then there are going to be receptors for hearing and balance inside that vestibulocochlear apparatus that are going to respond to separate stimuli and are going to be activated independently in the vestibule versus the cochlea. Again, depending on whether or not it's balance, that will be in the semicircular canals and in the vestibule, and then hearing, which would be primarily in the cochlea. So this will make more sense as we kind of get into all this. So again, this is just going through some of these structures in the ear and breaking it up into the external, middle, and the internal ear. Okay. And the new term for, they're always coming up with new terms for things, for the eustachian tube or auditory tube. You can call it the auditory tube. Their new term is the pharyngotympanic tube. But I will try to refer to it as the auditory tube. I'll try not to use eustachian tube, but please forgive me again. That was a term that was used for quite some time, and they just kind of recently got rid of it. I'm not sure why. I don't know the the origin behind changing the name for this, but I'll try to use both terms so that way then, you're associated with both terms. But again, if you're out there in the clinical world, you're probably still going to hear eustachian tube, because again, that was what many of these physicians learned many years ago. Okay, so again, external ear structures, we've got the auricle. As you probably know, it's got a lot of elastic cartilage covered with skin. Again, that's why you can kind of bend it, right, in these different shapes, and then it'll bounce back to its original form. It's going to funnel sound waves into that external acoustic meatus. And that external acoustic meatus is just this tube of cartilage and bone that's going to lead into the actual temporal bone. So it's going to lead here into that temporal bone into the inner ear. So that's what gets you into that the middle ear and inner ear. And it is coated with these ceruminous glands. These ceruminous glands, as you can guess, because we've talked about them before when we did the integumentary system, produce cerumen. That's earwax. And earwax ends up just being obviously this protective mechanism, a sticky trap for foreign bodies and insects, so things don't end up clogging up the tympanic membrane or end up causing issues where you have damage to that tympanic membrane because things are, getting into that inner ear or into that external acoustic meatus. So now what's interesting is some people produce a lot of cerumen from the ceruminous glands, and it can become a problem because you can get the buildup of the, cerumen on that tympanic membrane. And then some people don't produce a lot. And why that is, they don't really know. I have one of my sons, for some reason, he produces a lot of cerumen. And I actually have to clean out his ears every week because they just naturally produce a lot of cerumen. And I've actually asked his pediatrician about it, and she said it's just one of those things that they don't really know. Some people produce a lot of cerumen from their ceruminous glands, some people don't. And there's no real rhyme or reason that they can figure out right now as to why that is. And then this is, of course, the Mythbusters episode where Grant Imahara had to collect earwax and build a candle. Unfortunately, he's passed away now, but and he actually I think vomited when he was putting the earwax together. And just so you know, earwax did not make a proper candle. They ended up actually having to put a candle inside the earwax candle to get it to light there. So anyway, fun aside there, but then we have the tympanic membrane, which again is also kind of more commonly called the eardrum. This is the boundary between the outer and middle ears. And this is going to be where we're going to kind of transfer the sound waves that are coming into vibrations. And so it'll transfer that sound energy into vibrations in these little tiny bones called the auditory ossicles. And again, the order for those auditory ossicles will be the malleus, incus, and stapes in the inner ear. So I always tell people, if you're having because there's so much, right? And at the end of the semester, it's hard to remember these last bits of information. So if it helps you, you can remember MIS, M-I-S. So it's malleus, incus, and stapes. And so when we look at the middle ear here, so that was all external ear. When we get to the middle ear, where we have these auditory ossicles, again, here's your malleus, here's your incus, and here's your stapes. They say that the malleus looks like a mallet, hence its name. The incus is supposed to kind of look like an anvil, but it's really hard to see that sometimes. And then the stapes definitely looks like a little stirrup, which is nice. So you can think stapes stirrup. And the stapes is, just for fun fact, is the smallest bone in the body. So that the pharyngotympanic tube auditory tube or eustachian tube is going to be this tube here that is going to, maybe I'll kind of come back here, this tube here that is going to lead into the middle ear. And it's really important because, again, it connects our middle ear to our nasopharynx. Again, this is formally called eustachian tube. I would use that term loosely because in a clinical setting, you're probably going to still hear eustachian tube, okay? I don't know that there's many physicians that are ready to give that term up. It's, again, usually a flattened tube, but can be opened by yawning or swallowing. And that's why when you're, again, on a plane and you're going to be undergoing a pressure change, you want to allow that pressure to equalize in the middle ear and the inner ear with, again, the outside pressure. And the way that you do that is through this auditory tube. Okay, so you can yawn and that'll kind of open up that tube, or swallow really hard sometimes. Also, sometimes you can try, blowing, like plugging your nose and blowing really hard. And sometimes, again, that will open up that tube. Also, again, just like the action of chewing gum and swallowing will help to equalize that pressure in the middle ear with, again, the outside pressure. That's the big goal. And if for some reason you are congested, because this ends up, again, dumping into the nasopharynx, if there is inflammation along, the membranes of the nasopharynx, sometimes it will kind of partially block this opening here to the, see, I'm going to call it eustachian tube, the auditory tube. And then it makes it difficult to equalize the pressure in, again, your inner ear. And so that oftentimes can cause pain as that pressure kind of slowly equalizes. Usually it's not completely blocked. Usually, it will slowly allow that pressure change or that pressure equalization. But that's why you feel the kind of buildup of pressure inside when you're congested. The tympanic membrane cannot vibrate efficiently if there is a pressure difference on the sides here, meaning that if there is a pressure difference between here on this side of the tympanic membrane and you haven't equalized the pressure inside here, that tympanic membrane can't properly vibrate because, again, you might have, high pressure pushing that tympanic membrane out from the inside of the ear. So again, then when that happens, and you guys have probably experienced this when you've gone up an elevation and you haven't popped your ears, you can actually hear the sounds kind of distorted. And that's because, again, of that pressure difference, it's impacting the movements on that tympanic membrane. So kind of interesting. And again, here's those 3 auditory ossicles that you find in the middle ear: the malleus, the incus, and the stapes. Just really quick, the muscles of the middle ear that are associated with that, we have what's called the stapedius muscle, and it inserts on the stapes. It's really important because it prevents large vibrations of the stapes from really loud when you're exposed to really loud noises. And so that kind of helps prevent some of the damage that could occur due to, too large vibration on the stapes. And then we also have the tensor tympani, which is right here, and that's going to attach to the malleus, and that one is going to limit, obviously, the movements of the malleus and help prevent it from damaging the eardrum, because if it were to vibrate too much, it could, again, pull on that tympanic membrane or eardrum and damage it. All right, so now we're going to get into the inner ear and what we call the kind of membranous labyrinth of the inner ear here. And so as we move into the inner ear, we're going to get into this vestibulocochlear apparatus. And this is where, again, we're going to get our true sense of equilibrium here, and then our sense of hearing in the cochlea. So when we look at this vestibular cochlear apparatus, you're going to see, I'm just going to kind of go through some of the parts so you know the different parts here. So when we look at this portion here of the vestibular cochlear apparatus, we're going to see that we have what's called the vestibule in the center here. And then we're going to have these series of canals that are coming off called, there's 3 of them, called the semicircular canals. And these semicircular canals will kind of be at right angles to each other. We'll have the anterior, then we'll have the posterior, and the lateral one here. Now at the base of these semicircular canals, we're going to have these ampulla. And so we'll talk about those and some of how they're going to be important in terms of our creating our sense of equilibrium. Then we have this, what's called the utricle in the vestibule and the saccule in the vestibule. And so again, we'll talk about these associated with our sense of equilibrium. And then you'll see that we're going to have the vestibular branch of the vestibular cochlear nerve coming from the vestibule here. Okay. And then we have the cochlea here, which looks kind of like a snail shell. And it has these kind of this spiral appearance to it. And again, the cochlear nerve will come off of here and join the vestibular nerve to form the vestibular cochlear nerve. And then you'll see here that at the vestibule, this is where the stapes from the middle ear is going to come into contact with the vestibule here at what's called the oval window. Okay. So the vestibule, again, is going to be this kind of egg-shaped kind of labyrinth, and it's going to have these membranes inside. So it has 2 membranous sacs inside. One of them is called the saccule, and it's going to be continuous with what's called the cochlear duct that you're going to learn about inside this cochlea. And then we have the utricle here, which is going to be continuous with the semicircular canals that are associated with equilibrium. So these sacs house, again, our equilibrium receptors. Both the utricle and saccule will house equilibrium receptors that we're going to talk about that are going to respond to gravity and changes in the position of the head. We'll get into that when we talk about equilibrium. And then the semicircular canals are going to be these 3 canals here that we have. That are oriented in these 3 different planes of space. We're going to have our anterior, lateral, and posterior one. And inside the kind of bony canals, we're going to find the membranous canals with these semicircular ducts that are going to line the inside of each canal. And they're going to communicate with the utricle. So they'll dump into the utricle here. Again, which is important for our sense of balance. And then we have these ampulla here that are going to be these enlarged areas at the base of each of the semicircular canals, and they're also going to play an important role in equilibrium as well. They're going to have inside of them a structure called the crista ampullaris, and we'll talk about why that's important in your sense of equilibrium. So I'm just kind of introducing these terms now. And then these receptors inside here are going to respond to kind of what we call angular or rotational movements of the head inside these ampulla. Okay. So we'll talk about that and how the crista ampullaris. It's pretty basic. I'm not going to get into the nitty gritties on this. We'll be kind of pretty basic, but it's not too complicated in how they are important in our sense of equilibrium. But we're going to talk about equilibrium. We're going to come back and talk about equilibrium after we talk about our sense of hearing. So first, we're going to get into, again, the inner ear here and the cochlea. And the cochlea is going to be the portion of this vestibular cochlear apparatus that's going to be involved with our sense of hearing. So it's going to be this kind of small spiral. It kind of looks, again, like a snail shell. So it's a spiral organ. And it's going to extend from this vestibule, okay? And it'll coil, you don't have to know this, but it coils around this bony pillar in the center that they call the modiolus. But again, you don't really have to know that. It's not, so if you want to cross that off as a bit of information that I won't test you on, I'm not going to test you on that. And then inside you can see it's going to contain something called the cochlear duct, which is going to house our spiral organs or organ of Corti. That's going to be where we are going to convert that information from pressure waves in the inner ear to nerve conduction. Okay, so they're going to be, that organ of Corti is going to be kind of our primary organ that's going to kind of transduce our information coming into that inner ear into nerve conduction. Okay, and so again, this is going to be the anatomy of the cochlea, and we'll talk about kind of these different structures inside here. We're going to have these kind of series in each coil. You're going to have these kind of series of 3 canals here. We'll talk about in the and what they're associated with. So let me zoom in. If you could zoom into just one of these. So again, these are coils, right? So if you could take just one of these tubes of the coil and you could take a cross section of it, you would see inside that we have what's called the scala vestibuli and the scala tympani on the bottom. And you'll understand this more in a minute when we talk about how things move inside the cochlea. And then in between the two of them is going to be the cochlear duct, sometimes also called the scala media because it's in the middle. But most of the time it's referred to as the cochlear duct. And this cochlear duct is going to contain this very special organ of Corti or spiral organ. It's called both. And that is going to be that's really going to be associated again with transducing that information that's coming in as kind of pressure waves in the perilymph and endolymph here into, again, a nerve conduction through that cochlear nerve. So when we kind of take it, we're zooming in here. So when we zoom into this cochlear duct, we're going to see that this cochlear duct is going to consist of the basilar membrane, which is on the bottom here. So you can see this basilar membrane is going to be right here. And then you're going to see that this is going to be this kind of organ of Corti or the spiral organ. And it's going to contain these hair cells. There's outer hair cells and inner hair cells. I'm not going to get into, because of time, we're not going to really talk about the difference. I do have a slide on it and you can read about it, but we're not going to really talk about we're not going to separate out the hair cells into the outer hair cells and inner hair cells because it just gets a little more complicated than we need to get. So we're just going to talk about the hair cells in general. And these hair cells are going to be attached to these little tiny hairs that are sticking off of them, hence the name hair cells. And these little hairs sticking off of here are oftentimes what we call stereocilia, okay? And these stereocilia will be associated with creating graded potentials inside these inside these hair cells as they move, as they're moved because of, again, movements from this on top called the tectorial membrane. So again, you can see this is kind of a spiral organ. It kind of spirals around here, and then it has this tectorial membrane that's going to kind of spiral on top. When it comes around here on bottom, it's the basilar membrane. And so as that tectorial membrane is moved, due to, again, some movement in the endolymph here. As it's moved, it will move these hair cells and then create graded potentials that will eventually, again, be stimulating these first order neurons of the cochlear nerve. Okay, so gives you kind of a quick little overview. And this is just a scanning electron micrograph, kind of interesting to see what they actually look like of these hair cells. Okay. So let's first, before we get into the nitty gritties on sound, let's talk a little bit about sound detection. So again, hearing is technically just the kind of reception of the sound waves in the air that are then going to be converted to this fluid pressure wave inside the cochlea. And that fluid pressure wave is what's going to ultimately stimulate these mechanoreceptors, those hair cells inside the cochlea, that will then kind of convert that to an impulse, right? A nerve impulse that can be sent back to the brain. And so that's kind of the big overview of how hearing happens. And when we talk about sound itself is going to be basically a pressure disturbance, and it's going to alternate, areas of high and low pressure. And we'll talk about how that happens. Produced by, again, vibrating objects, and again, propagated or moved by molecules of the medium, which is our air. Okay, so basically, again, we are, when we are hearing things, we're converting, again, those sound waves into fluid pressure waves, and then eventually into, again, nervous conduction. So we're going to talk about, sound travels in, again, a wave format. And so as that sound travels, there's a couple of, terms that we're going to use that are associated with looking at things that move, a certain distance with a wave-like motion. And that is, we're going to talk about wavelength. So when we look at an actual wave, you guys probably know the crest of the wave is the top and the trough of the wave is the bottom. And so when we're looking at wavelength, how long one wave is, we're going to do something like crest to crest, okay, or trough to trough. That's one wavelength, okay? So wavelength is going to be important because we're going to talk about things like frequency, and that wavelength will actually determine what frequency we're hearing. And then amplitude is going to be how high this wave is. Okay, so this is amplitude right here. So as you're going to see, the higher the amplitude, the louder the sound is. The lower the amplitude, the lower the sound is. Okay, so let's talk about these two major terms that we have to understand: frequency and amplitude. Okay, and again, I'm going to go through these probably rather quickly because most of you probably already know these two properties. So frequency is going to be the number of waves that pass any given point over a certain time, okay? And so frequency, again, is going to be associated with our wavelength. And again, the wavelength is going to be the distance between two consecutive crests, or, you could do two troughs, okay? So the distance, again, between those separate sets are wavelength. Now, you can see here that the wavelength here is much longer than it is here, and the wavelength here is much shorter. And so a shorter wavelength like this, guys, is going to be associated with higher frequencies of sound. So you can see this is a 15 hertz sound. Higher frequencies, shorter wavelengths. You probably kind of already know this. And then the longer wavelengths are going to be associated with lower frequency sounds, okay? So again, this is going to be, here's shorter wavelengths, high frequency, and then lower, again, frequency is going to be these longer wavelengths, okay? So hopefully that'll help you kind of remember that. And, if we have a pure tone, then we have the same wavelength, okay? So a tone is going to be, again, a certain frequency that's, repeated over just like this, okay? So frequency range for human hearing is anywhere from 20 to 20,000 hertz. But most people, again, are sensitive to sounds between 1,500 and 4,000 hertz. 20 hertz is kind of on the the lowest frequency range for humans. And Pitch is just our perception. When we say the term pitch, like high pitch, it's our perception of different frequencies. So if we have a high pitch, then we have a higher frequency. So again, high pitch, high frequency, low pitch, low frequency. Okay, so that's what pitch is when we use that term. Quality is just the characteristic of the sound. Again, this is kind of a little bit subjective. Most sounds are a mixture of different frequencies. And then a tone, remember, is just where we have just one frequency. And sound quality, again, is going to help provide our richness and our complexity of our sounds, like we hear in like music. Okay. So again, this is just kind of going through here frequency. So here you can see again, this is a higher frequency. So obviously a higher pitch in red, and then the blue is going to be a lower frequency. So again, lower pitch. And then you can see that both of them have about the same amplitude, which is going to be your sense of how loud something is. So that's our next term, amplitude. And that's the height of the crest. So again, how tall this wave is. And that amplitude is going to be perceived as loudness. Obviously, this is going to be kind of subjective to, the sound intensity in terms of the individual's interpretation of that sound intensity, whether or not it's loud or, not so loud. That'll be different in each individual. This is going to be measured in decibels. And so the normal range is for, again, sound is 0, which would be, again, complete quiet, to 120 decibels. And so normal conversation is around 50 decibels. And then the threshold for us, but that where it's the kind of our threshold of pain, and also our threshold of kind of where that point where we could do damage to some of the structures in the inner ear is about 120 decibels. So severe hearing loss can occur with prolonged exposure to anything above 90 decibels. That's why if you work in a job, where like you're working around aircraft and the sound that you have every day is above 90 decibels, then you have to wear some type of, again, sound muffling earphones or something like that to protect your ears. And amplified rock music is usually, like if you're at a concert, is usually 120 decibels or more. So again, this is just showing you the difference in amplitude. So here, again, you have, a really loud noise because you have a high amplitude. And then here you have a really soft one. Again, low amplitude. Okay? So what's cool is you can see this. I know you've seen this in, if you've ever used the microphone or things like that on your computer, and they kind of can transfer this into, kind of graphical form that we can see. And you can see here, again, louder noises, again, are going to have these higher amplitudes. So this is loud. This in between is quieter. And then, again, you can see these are spaced really close together. You can't even see any lines in between. So that means that here you have a really high frequency because the wavelength is really low, where here, you have a greater wavelength here, so you're going to have a lower pitch, okay? So here, this would be, your higher pitch, and then here would be your lower pitch, where they're more spaced out here, okay? So kind of interesting. So let's talk about the pathways of sound waves. This, again, I'm going to try to stay fairly basic here. So there is this fluid in the inner ear, and I want to kind of review the structure here of the cochlea. So if you look at the cochlea, and they kind of simplified the coils. Remember, it's more coiled than this, but they kind of simplified this so that you can see what's happening in these interior structures inside the cochlea. So that's why it doesn't look as coiled. And so I just want to kind of go over some terms here. So here, the stapes is going to contact the cochlea here at what's called the oval window. And that's where it's going to transfer those vibrations into these pressure waves in this fluid inside here called the perilymph. Okay. Now, and I don't necessarily care that you know the term perilymph, but I do want you to know that it's a fluid inside the cochlea. So now when we look inside the cochlea in each one of these coils, remember that we're going to break this up into these 3 different canals. We're going to have the scala vestibuli on top. We're going to have the cochlear duct in the middle. And then on the bottom is going to be the scala tympani. Okay, so kind of keep those in mind. And then remember, it's inside the cochlear duct that we're going to have those spiral organs, or the organ of Corti. So we're going to just keep really basic to this, okay? So when we have, again, a sound wave that's vibrating these auditory ossicles, it's going to vibrate that stapes, and then at the stapes, and again, remember this is originally, sorry if I should start way back here, originally that sound wave comes in, right, in that waveform, hits the tympanic membrane, vibrates the tympanic membrane, and then that as that tympanic membrane vibrates, it's going to vibrate the malleus, the incus, and the stapes, okay? The reason that we have these structures in the inner ear is that they actually amplify the vibrations, and then they're going to, again, transfer those amplified vibrations into pressure waves at this oval window. So at the oval window, the stapes is then going to vibrate, and it's going to vibrate against the oval window, creating these pressure waves in the fluid on the other side, in the cochlea. And that's going to occur, so that oval window is going to meet the cochlea at the scala vestibuli, okay? So it's not down here in the tympani, it's only, again, meeting the fluid of the scala vestibuli. So again, it's that pressure wave is going to be created by the stapes when it pushes on that oval window, and then as it does, it's going to create a pressure wave in the scala vestibuli. Now that pressure wave will move through this scala vestibuli. Now, if that pressure wave is 20 hertz or lower, and that's going to be this first case here, this first case here in 4A. If that pressure wave is 20 hertz or lower, which remember, again, we can't hear below 20 hertz. The reason is that pressure wave is just going to continue on down the scala vestibuli until it hits what's called the helicotrema, which is the very tip here, where it's going to move around the cochlear duct and then go down the other side. And remember, the other side is going to be the scala tympani, okay? So again, sound with frequencies below our hearing level, below 20 hertz, are going to move through the scala vestibuli all the way down around the helicotrema, and they're not going to excite any hair cells inside the cochlear duct, okay? So that's why, again, 20 hertz and below isn't, we can't hear it, okay? And what's going to happen is then that pressure wave is going to move here through the scala tympani, and eventually here it will be kind of dispersed at what's called the round window. And this just is a way for us to keep sound waves from, or pressure waves from moving back and creating confusion. So it's only going to move in this one direction, this way, and then eventually out here, and then again, be distributed out through that round window so it doesn't bounce back. Okay. Now, if we're able to hear a sound, that means that this sound is going to be moving through the cochlear duct. And where it moves through this cochlear duct is going to depend on the frequency of that wave. So higher frequency waves will actually move through the cochlear duct up here, and lower frequency waves will make it much farther and move down here. Okay, so what happens here is these sounds, again, as they're moving through the scala vestibuli, they're actually going to move through the cochlear duct, and we'll talk about how this happens at this kind of right frequency, okay? And then they're going to vibrate through what's called the basilar membrane, which is on the bottom of that cochlear duct here. Or the basilar membrane, and then they're going to make their way through again, that cochlear duct through the basilar membrane. When the basilar membrane is moved, it's going to deflect some of the hairs on those hair cells, push them up against that tectorial membrane that we're going to talk about in just a minute. You can't see that here. And then that's going to create the nerve conduction. And then eventually, again, that pressure wave will then be dispersed through the scala tympani and out the round window. Okay, so that's the basic pathway of sound. Okay. And I'll kind of go through this at the very end and kind of review this. So resonance is just the movement of different areas of the basilar membrane in response to a certain frequency. And so that basilar membrane that's going to run along the bottom of that cochlear duct is going to have fibers that have a different kind of range of stiffness. The fibers that are really close to the oval window are going to be really short and really stiff. And what that means is it needs more energy or a higher frequency to move those, okay? So these fibers that are close to the oval window that are short and stiff are going to resonate with high frequency waves. Okay? The fibers that are going to be near the cochlear apex or kind of near the helicotrema are going to be longer and floppier, and they're going to move a lot easier. So we don't need as much energy to move them, so they're going to resonate with lower frequency waves. And so as you can see, this is going to be really dependent where along that basilar membrane you can, resonate those or move. That membrane is going to depend very specifically on that frequency. Okay? So the basilar membrane, again, once it's moved, okay, by that correct frequency, then it's going to mechanically process that sound before, again, the signals reach the receptors. We're going to talk about how it does that. Okay. It's already doing that because it's processing that sound based on the correct frequency. So I like this. This is a really good, I feel like, visual depiction of what's happening on that basilar membrane. So the basilar membrane here, again, is going to be on the bottom of that cochlear duct, coiled up inside the cochlea. And so let's uncoil it. If we could uncoil it, this is what that basilar membrane would look like. Again, short, stiff fibers are going to be towards the base of the cochlea. And then at the end of the coils here, towards the apex and the helicotrema here, we're going to have these long, floppier fibers. Okay. So again, as a result, different frequencies are going to vibrate the basilar membrane in different places. So again, this here would be stimulated to move by those really high frequencies, here in the middle, mid frequencies, and here at the end, low frequencies. Okay. So this is just kind of showing you this. High frequency sounds are going to displace the basilar membrane near the base of the cochlea, medium frequency sounds near the middle, and then low frequency sounds near the apex where the helicotrema is right here. Okay. So just kind of, again, interesting how it's always amazing to me, again, that this all happens at this microscopic level inside our ears. And again, that not more goes wrong because it's really so complex and even more complex than we're getting into. Okay, so now when we look inside that cochlear duct, and we're going to take a closer look at that. Again, we're going to see that on top of that basilar membrane, we're going to have this, remember, spiral organ of Corti. The organ of Corti, or spiral organ of Corti. I like spiral organ of Corti because it kind of combines both of them. So you can see that basilar membrane is going to be here on the bottom, and then it's going to eventually kind of wrap around here and form this tectorial membrane that's on top. So as that basilar membrane here is moved, okay, and it pushes up. So as that pressure wave moves through the cochlear duct and moves this basilar membrane, as it does, it's going to push this up and you're going to see it's going to push these hair cells with these little stereocilia up against that tectorial membrane, moving those little stereocilia. Now, when it does that, these have little mechanoreceptors here. So when you move them, they're going to trigger these little mechanoreceptors, these gated channels to open when they move. And that's going to allow a depolarizing graded potential to occur. And if you get enough of a enough of a depolarizing graded potential to occur, then it's going to pass on excitatory neurotransmitter to these associated neurons that are eventually, again, the axons are going to make up the cochlear nerve. So then they'll excite again and create an action potential in those neurons, and that information will be sent back through the cochlear nerve to the brain. So that's how it all happens. This is more than I'm going to get into because we just don't really have time to go into. If you want to look at exactly how those bent hair cells are going to kind of transmit that information, we kind of just talked about how they kind of are going to mechanically open these gated ion channels and create the action potential. It's a little more complex in terms of which way the hairs bend, but I'm not going to get into that because it's just more complex than we need to. So at the level for us that we need to know it at, I just want you to know that these stereocilia are moving against that tectorial membrane when the basilar membranes moved in that certain area for that certain frequency. And that's what's going to stimulate that graded potential in here, and then eventually an action potential in the nerve fibers of the cochlear nerve. Okay, in that section. So you're going to see that there's different sections of the cochlear nerve for different frequencies along the basilar membrane. You know, here, if you're back over here towards the base, and, you know, then you're going to have spiral organs of Corti back here that are going to be stimulated. Or again, and that would be for high frequency. If you're low frequency, it's going to be, you know, down lower here on the basilar membrane. And so you're going to have different nerves at different levels, branches of the cochlear nerves at different levels of that basilar membrane that are going to be associated with different frequencies, if that makes sense. So again, I told you we're not going to get into the kind of fine tuning of the outer hair cells versus what the inner hair cells do. You're welcome to kind of get into this, and it talks about these inner hair cells and how they kind of protect you from loud noises. But I'm not going to test you on this because we just don't have the time to get into it. It's more important that you kind of understand the big picture of it. So again, as these hair cells again are exciting these sensory neurons of the cochlear nerve, that information is what we call the auditory pathway. That information is going to be passed again along the axons of these cochlear neurons through that vestibulocochlear nerve, okay? And then they'll come into the brain through the medulla, okay? They're kind of synapse with a second order neuron, and then some of them even with a third order neuron that will take it all the way up to the thalamus, the relay center, and then on out to the primary auditory cortex. Okay. So basically, again, I'm not going to, get into the nitty-gritties of how this moves through here, but I do want you to know that it goes from the vestibulocochlear nerve up into that primary auditory cortex, where we're actually processing the sensation of that sound and that high pitch versus low pitch, again, loud versus soft noises. Okay. So this is just an overview of kind of the physiology of hearing at the level. I just put this in here so that it's at the level that I want you to know. So again, the auricle, this is kind of the big picture, starting back with the sound being funneled in through the auricle. It's going to collect the sound waves. And then those sound waves are then going to vibrate the tympanic membrane, the eardrum. Slow vibration in response to low pitch sounds. Rapid vibration in response to high pitch sounds. Those ossicles are then going to vibrate since the malleus is attached to the tympanic membrane. And then it'll move through the malleus, incus, and stapes, where it amplifies those vibrations. Then the stapes is going to push on the oval window, producing, again, a fluid pressure wave in the scala vestibuli. And then eventually, again, it'll move out through the scala tympani, eventually to be disperse that sound. Then that oval, I just kind of put this in here, is kind of interesting. The oval window vibration is actually 20 times more vigorous than what it initially was at the tympanic membrane. So this is how, again, we kind of amplify that vibration so that, again, we can have kind of a more fine-tuned response to sound. So pressure fluctuations, again, inside that scala vestibuli are then going to move through the cochlear duct depending upon our frequency, right? And they'll move through that basilar membrane and then push those hair cells inside the spiral organ against the tectorial membrane, okay? And when they do that, then those little hair cells, the stereocilia, are going to be bent, and they're going to produce a receptor potential in those hair cells that will then trigger an action potential in that nerve that it synapses with, the cochlear nerve that it synapses with. So again, the pressure fluctuations of the endolymph are going to move the basilar membrane. And as they do that, they're going to move those hair cells of the spiral organ against the tectorial membrane. The bending of those hairs is going to produce receptor potentials. That's going to lead to the generation of nerve impulses in the cochlear nerve fibers. Okay? So that's how sound happens. I'm going to try to post there's some great videos that go through this whole process in like a 5-minute animation. So I'm going to post those for you as well when I do the announcement for this. So really briefly, we're going to talk about our maintenance of equilibrium as well. Because this lecture, again, is running a little bit longer on the longer side because I covered some lab things in here, I'm going to try to, again, keep this fairly basic, fairly superficial. So our equilibrium, again, our sense of equilibrium is going to be a response to various movements of our head, okay, that are going to rely on input from our inner ears. It'll actually take into account, as you're going to see when we talk about things like motion sickness and getting mixed messages, from our eyes as well as stretch receptors. So there's more than just that vestibule apparatus that's going to be associated with our sense of equilibrium. Again, we'll talk about that, how our vision and stretch receptors actually comes into play at the very end. So, but here we're going to primarily, because we're talking about the inner ear, focus on the vestibular apparatus. Okay, so inside the vestibular apparatus, we're going to have these equilibrium receptors in the semicircular canals as well as the vestibule. And that where we have those receptors is going to depend upon the type of equilibrium that we're detecting. So vestibular receptors, which is just receptors in our vestibule, are going to monitor what's called static equilibrium. And this is kind of exactly kind of what it sounds like. This is going to monitor our linear acceleration and the position of the head with respect to gravity. So this is called static because our gravity is constant, okay? And so because of that, this is going to monitor again that, acceleration of the head and the position of the head, if it's side to side, with our respect to gravity. Now, our semicircular canals are going to be these receptors that are going to monitor dynamic equilibrium, which is going to monitor changes in our head rotation. So are we turning it to the right really fast? Are we turning it to the left really fast? That's going to be picked up by your semicircular canals. But your static equilibrium is just going to be the position of your head kind of with respect to gravity. So, is gravity pulling more on the right side down? Is it pulling more on the left side down? And so that's kind of where, and this might make more sense as we kind of go through it here. So again, we have these semicircular ducts here.
And so remember that when we were talking, about static equilibrium, so static equilibrium is going to happen in our vestibular receptors. Oh, there we go. So our vestibular receptors are going to be in the utricle of the vestibule here and the saccule. So these regions where we have those receptors are called the maculae. Okay, so that's where we're gonna have our sense of static equilibrium, and then our sense for dynamic equilibrium is going to be found in these ampullae. Okay, in these organs that we call the cristae ampullaris or crista ampulla. Okay, so let's first talk about static equilibrium. So the sensory receptors for our static equilibrium are going to be these maculae inside the vestibule. Okay, here's the maculae inside the vestibule. And these maculae, there's one inside the saccule and one inside the utricle. They're going to monitor where your head, the position of your head in space. Okay, so is gravity pulling down if you turn if you put your ear to your left side? Is gravity pulling more down on one side of your head versus the other side? That's going to be how you monitor the position of your head in space. And this plays a really key role in helping us control our posture. So again, we're going to be responding to these linear acceleration forces kind of in one direction, not rotation. So not like moving your head quickly to the right, moving your head quickly to the left. That's dynamic equilibrium, okay? So again, those are, sorry, and I already kind of jumped ahead and showed you where everything was in here. So again, we're focusing on the maculae in here, the vestibule, both the utricle and the saccule of the vestibule here. So let's talk about what's inside these macula and how they work. Inside each of these macula is this kind of flat patch of epithelium that contains hair cells. Okay, so again, as you can see, our theme here, right, is these what we call stereocilia hair cells. And so we're going to have lots of these just regular stereocilia. And then we're also going to have these kinocilium, which are our true stereocilium. And they're going to be really important in terms of detecting, again, and stimulating that nerve conduction. So it's important to know that you have these shorter stereocilia and then these long kinocilium, okay? And the stereocilia are going to be embedded in what's called this otolith membrane. It's this gelatinous mass here. So here's your otolith membrane. And it's just like, it literally looks like this like layer of jelly. And in that like jello, it's kind of this like jello consistency. In that jello, we have these otoliths, okay? Otolith literally is what it sounds like. Auto means ear, lith means stone. So these are your ear stones. And these otoliths can move, right, within this jelly-like material, the otolith membrane, depending, come on, again, which way you move your head, right? So these otoliths are just these little calcium carbonate stones. So literally, hopefully that helps you remember them. Lith means stone. So again, ear stones. And so we have, again, these otoliths, and they're going to increase the membrane's weight and increase its inertia or resistance to changes in motion, depending upon, again, which way you have moved the position of your head. So let me show you how this works. I'm a visual person, so hopefully this will help out a little bit. So again, here are going to be these hair cells. They have, similar to the hair cells in the cochlea, they're going to have these stereocilia, but then each hair cell is going to have one kinocilium, okay? Now, if you have your head upright, okay, then you're just going to get this steady stream of action potentials through these hair cells that are going to be, again, kind of sending those action potentials at a regular, steady rate, okay, if you keep your head upright. Now, if you tilt your head forward, when you tilt your head forward, you're going to see that these stereocilium hairs are going to bend towards the kinocilium as those otoliths, right, because of gravity, are going to pull this way, okay? And as they pull that otolith membrane, that jelly mass, it's again going to force these stereocilia to bend towards the kinocilium. So the hair is going to bend toward the kinocilium. That's going to cause this hair cell to depolarize, and then it's going to cause it to excite that nerve fiber and send an action potential at a faster rate down that vestibulocochlear nerve. Okay? So this is all I want you to know at this level, okay? And no more, because we, again, just don't have the time to get into all the nitty-gritties. If you tilt your head backwards, it's going to be just the opposite. So now gravity is going to pull those otoliths in the opposite direction, pulling again that gelatinous otolith membrane this way. That's going to force the hairs to bend away from that kinocilium. And now it's going to cause those hyperpolarization inside that cell. So it's going to cause an inhibitory graded potential, hyperpolarization. So the nerve fiber is going to be inhibited and the action potentials are going to be slower. Okay, they're going to move at a slower rate down that nerve. Okay? So that's all that's happening. And that's what tells us, whether or not our head is upright, tilted forward, or backwards. And obviously there's many gradations in between as you move your hair, you move your head again in between that forward and backwards. Okay. So that's basically how we're detecting our static. That's how we detect our static equilibrium. Now, how we detect our dynamic equilibrium is going to be a little bit different, okay? So we have different receptors for what's called a rotational acceleration. And so this is going to be our dynamic equilibrium. And this is going to be found in the ampulla of those semicircular canals. There's going to be a structure called the crista ampullaris. So let me go back to these semicircular canals. So here you're going to look at these semicircular canals at the base of them, that where they connect to the vestibule, is going to be these ampulla, this kind of like, bulge here. And in those ampulla, we're going to find the crista ampullaris. And the crista ampullaris are going to be the organ for dynamic equilibrium. The cristae are going to be excited by acceleration and deceleration of the head. Okay, so again, a major stimuli is going to be your kind of rotational movement, such as twirling the body, twirling the head. Okay, and so these semicircular canals are located on all three planes. So these ampulla the cristae ampullae can actually pick up on all rotational movements of the head because it's going to be in these three different planes. So here's the structure that, again, is that cristae ampullaris is going to be here. And the cristae ampullaris is going to consist of all those hair cells here, okay, that are going to be bundled together. And just like before, these hair cells are going to be bundled together with a kinocilium plus the stereocilium. This is just a scanning electron micrograph of that. And so what's going to happen is at rest, what's called the ampullary cupula, which is going to be this structure that kind of sits on top of all those hair cells, is going to stand upright, okay? Now, during rotational acceleration, the endolymph is actually going to move inside this cristae ampulla in the opposite direction inside the semicircular canals to the actual rotational movement. And that's because it's going to lag behind due to inertia. So again, as you start to spin here towards the right, the endolymph is going to move in the opposite direction towards the left. And that endolymph flow is going to bend that cupula and excite the hair cells, okay? Now, as rotational movement slows, then the endolymph will actually change directions and keep moving then in the direction of the rotation. And then that endolymph flow will bend the cupula in the opposite direction. So again, now you're slowing down and it's going to inhibit the hair cells, okay? So kind of interesting. So how that happens. So again, we're gonna keep it pretty basic here. Because this is last minute, it would probably be like a true false question on this, just to give you an idea. Again, because I know I don't have a lot of time to talk about that. And so, but I really want you to know that this Christie ampula is associated with our rotational movement. Okay. That's the basis on how it does it. But I'm not going to get into the nitty gritties on that or ask you a nitty gritty test question on these last minute things. So remember that for our sense of equilibrium, we're bringing in information from both the vestibular receptors, our visual receptors from our eyes, as well as some of our somatic receptors that are giving us an awareness of where different parts of our body are in relationship to our head. And so all of that information is going to be brought into the brain and be processed in that same area in the brain stem. It'll also be passed on to the cerebellum as well. And this is going to give us our overall sense of balance and orientation. Now, this becomes a problem that all of three of these have an input. These are all three sensory inputs that are fed into kind of our major processing area for our equilibrium, because sometimes we get basically a mismatch of that sensory input. And this is what happens for those of us that get motion sickness. Those of us that get motion sickness can't tolerate this mismatch of information coming from, for example, in this case, for motion sickness, from our visual input versus our equilibrium input. So what happens is, in this case of getting motion sickness, like while you're riding a car and trying to read, if you're riding in a car and trying to read, you're looking down. And so when you're reading and looking down, your visual input is telling you that you're not moving, okay? Because you're reading the stationary book. However, again, your vestibular apparatus is telling you different, okay? And so that input coming in from this vestibular apparatus is saying, hey, we're moving. Visual input is saying, no, we're not moving. And that conflicting information is what causes motion sickness. Now, the real trick here is, why does that conflicting information cause motion sickness in someone like me and possibly not in you? And there's the real trick. We don't really know why. It's how it's processed in the brain, right? But it is that conflicting information that gives us that motion sickness. So this is why they typically tell you, as you start to feel motion sickness, try to look up and look at the horizon, and that it gives that your visual input that sense that, okay, you're moving, and it will help to match the input that's coming in again from that vestibular apparatus. So warning signs that you're feeling, you probably know this, that you're feeling motion sickness, that you have excess salivation, pallor, rapid deep breathing, profuse sweating, all things you probably know. And then you can treat this with, obviously, like anti-motion drugs. So meclizine is one, which also is called more commonly Dramamine. So meclizine, Dramamine. And what basically these anti-motion drugs do is they depress that nerve conduction through the vestibular input. So they kind of depress your vestibular input, okay? So that's how they work. So again, meclizine, scopolamine is also another one. I think that one actually is... you put it as a patch on the back of your ear. So those are some of the different anti-motion drugs. Now I'm going to talk about this syndrome called Meniere's syndrome, and mainly because, one, it's in your book, also two, because I actually developed Meniere's syndrome 2 years ago. So it's kind of an interesting story. So Meniere's syndrome is what we call a labyrinth disorder. It seems to affect actually all three parts of the inner ear. And it's still kind of, again, not a lot is understood about Meniere's, because it seems to be caused by different things. But the main result from these different causes is usually an increase in the endolymph fluid inside again that labyrinth of canals in the inner ear. And so the symptoms for this are going to be attacks of vertigo, and it is pretty severe vertigo. Mine came on very suddenly a couple years ago, and when they say your balance is so disturbed that standing erect is nearly impossible, that is true. I had trouble even making it across the way to the bathroom. Because the vertigo is so intense. It's very weird. It's a very weird sensation. And then, of course, because of that vertigo, it causes nausea and sometimes vomiting. And so I also had another major symptom that's associated with Meniere's, which is because, remember, that endolymph is not only just in it's not just in the vestibule and the semicircular canals, but it's also, remember, running through the cochlear duct inside the cochlea. So a lot of times it'll cause issues with hearing as well. So I had the tinnitus. It was really loud in one ear. Tinnitus is just that ringing inside the ear that you get, the ringing or buzzing sound. And it was really loud, so much that it actually impaired my hearing. And I actually ended up, because of that increased pressure in the endolymph, it actually did some damage. And I actually lost some of my hearing. But interestingly enough, for whatever reason with Meniere's syndrome, you lose your hearing in those lower frequencies. Maybe it's because, again, that basilar membrane is again, kind of looser and more flexible in that. Why I'm kind of guessing, they don't really know, but you do typically lose hearing in the lower frequencies. Sometimes you'll get it back when the endolymph levels decrease back to normal, but not always. And mine, actually, I ended up getting some permanent loss just in the lower frequencies. So, and so the treatment is actually, you can take meclizine. You can try a low salt diet, which will again hopefully decrease your fluid levels along with decreasing the endolymph fluid. And then for me, I put this in here, didn't have it in your textbook, but they find that some individuals, Meniere's is stimulated as an autoimmune response. Again, the mechanisms on how that works are not understood. But for me, steroids worked. And so as soon as they put me on steroids, within a day, my vertigo was gone. I slowly got back my hearing over, the course of the treatment. And so I just added this in here because it's kind of interesting. And I have that kind of personal experience with it. And you may know someone that has Meniere's. It's kind of being more commonly diagnosed now. Now, in really severe cases, they can actually drain the endolymph from that internal ear. And then as an absolute last resort, they can actually remove the entire malfunctioning labyrinth that's causing the problems. But obviously that they don't want to do that. So again, most often it usually comes in kind of waves and yeah, kind of interesting. Okay, a couple other homeostatic imbalances. Conduction deafness. This is conduction deafness is just like it sounds. It's an impairment where we block the sound conduction to the fluids of the internal ear. So you're blocking the conduction from like sound waves to like vibrations, okay? So this oftentimes can be caused by some type of damage or some type of problem with the tympanic membrane. Maybe the tympanic membrane has a bunch of earwax on it and it can't move properly. Maybe you actually perforated the tympanic membrane. Maybe you have something called otitis media, where you have an infection in the middle ear and it's caused fluid in the middle inner ear, and that's pushing against the tympanic membrane. It can't move properly. And then sometimes you can get what's called otosclerosis, usually in older individuals, of the ossicles, where the ossicles kind of get these weird growths on them. And then the stapes actually fuses to the oval window. And so obviously that it's stiffer and causes issues with conduction. So sensor neuronal deafness is nerve deafness. This is what you consider to be nerve deaf. And this is any damage to the neural structures that are associated with the cochlear hair cells, okay? So any point from cochlear hair cells to the auditory, again, cortical cells in the brain are going to be associated with nerve deafness. So again, this is going to be damage to that nerve pathway, or again, the sensory receptors, the sensory hair cells inside. And this typically happens because of gradual damage to those hair cells, okay, over time. So again, as we get older, we get damage to those hair cells, the stereocilia. And so that'll cause some of our sensory neuronal deafness. Now, deafness due to destruction of those hair cells, we now have cochlear implants for that. And the cochlear implants are basically like replacing the cochlea. So again, there's a little microphone, there's a microprocessor, there's electrodes in there that are going to all translate sounds into electrical stimulation on that vestibulocochlear nerve. So it basically is trying to do what the cochlea does for you. And it is artificially inducing that nerve signal. So it's not as good as our cochlea. Obviously, it provides kind of crude representations of sounds. But if, you're like, my cousin has a daughter who was completely, basically completely deaf, those cochlear implants give her some sound. And so going from completely deaf to, again, crude sounds, and the cochlear implants are getting better and better. So, she can talk to you now, and it's pretty amazing where she went from having to, use sign language to being able to talk to people and be able to hear them and understand them. So it's pretty impressive how far cochlear implants have come. And this just talks a little bit about, again, how some of these senses, as you can guess, many of these senses, again, due to kind of deterioration of the receptors. So again, things like vision, hearing, taste, and smell are all going to decline as we get older because, again, obviously those receptors are going to, decline as well. So that's the end of the lecture. If you have any questions for me, please let me know. And again, like I said, I'm going to try to kind of stay more at the basic level for this lecture because I know it's your last one right before the final. Please let me know again if you need to set up some time with me as well, and I will set up some time to meet with you. And that's it.